This coming slide, I will show you the effect of the damping ratio on the nature of response. Underdamped response is where your zeta is between 0 and 1. So let's look at one transfer functions. Gs, our input is the step input, 1 over s. So when we have Gs and then we put this, the root, you factorize this one, you can get your S1 and 2 is at this location. So this one and this one. So if we want to see the step response, Rs is S at the bottom, so means it's a pole. So pole S equals to 0, so you mark the cross mark at the 0. So to see the performance of this, you always can see this is the underdamped response. So for the level of undergraduate study, you learn the rise time, settling time, peak time, overshoot, and so on. All these equations, this formula, we use the underdamped response to derive them, because only the underdamped response you can see those characteristics. Next is undamped response. Undamped response, undamped, from the word you can see that un is no, so no damping response, so which is the zeta equals to 0. So when this happens, let's look at the step response where 1 over s at 0. This is our undamped response when zeta is very small and nearly 0 value, so you can see the system oscillate much. So this is the third one, critically damped, means it's very high damping. So we assume this zeta is at equals to 1. So when this condition happen, usually is 2 roots happen on the real line. So let's look at the step response of this is undamped. When we have sufficient damping characteristics, the system without oscillation and is steady in this way. So I want to tell you here that there is none of the best responses. There's only have the suitable response for the certain system. This slide will show you the responses with different of the nature response, the damping characteristics, where the zeta is very small, you see very high oscillation, to the overdamp, when the zeta more than 1, the system actually moves slower, as you can see. Okay, so another word we can say that when zeta is small, the system oscillate much. It might go faster, but it might easily tends to oscillate. But if the system have the too high or high damping zeta, the damping characteristics, the system will not oscillate, but it will move a little bit slower than we expect. So for the certain system, if one of the system you want it to move faster, but it's naturally born in this way, slower with very high damping characteristic, means maybe the friction characteristic is high, so you need to design some of the controller, suitable controller to make the system become faster. So this is responses is very important for us to evaluate it. This example is let us to find the zeta and omega n based on this closed loop transfer function. So it is very simple example that I just need to show you that there's nothing here, so this follow the standard one. Then this 36 is omega n squared. So you do the mathematics, you can get 6. So here is 2 zeta omega n equals to 4.2. Then you already have omega n here, so you can get the answer. Okay, So before a control system is designed, specification must be developed that describe the characteristics that the system should possesses. So like I said just now, we always use the underdamped second order system to diagnose or to evaluate and to tell the story of the performance of our system. So for here, you need to know is first is the rise time. Rise time always tell you how fast your system move. So rise time, you can see that is from the 10% of your responses to the 90%. Okay, here you look it's a 0 0.1, 0 0.9, 0 0.1 because the final value is 1. But if today your final value is 5, it doesn't matter. But remember, it's no longer 0 0.9 here, no longer 0 0.1, but it's still 90% and 10%. Okay, so TP is the time when the highest peak happened. So MPT is the magnitude peak. The highest magnitude happened at what value and at what time. This is the peak time. So settling time is usually we will put plus minus 2% to set the system of the output for the responses to settle down. So then only you can get what is the TS. So a good system, when it's very high oscillation, definitely they will have the longer setting time. If your system or your controller can make the system reach faster to destination and also settle down faster, then that is the good control system. These all are the formula to help us to get the value or to evaluate the settling time, the peak time, overshoot, and so on. So you can see there are two ways to calculate the overshoot. Where you've been provided by the step responses, you can use this one. But if you don't have the step responses, but you have the value of the zeta, then you can use this formula. Both can give you the answer of overshoot, peak time and the setting time. So for now, I think no matter it's the open book test or closed book test, this formula always be provided for you. Let's look at this example. For the system shown in this figure 6, we have to do the following. So this is a very simple second order system. Why second order? Because we have one mass here, we have one damper, and we have one spring. So first question is find the transfer function x over f. So then we need to get this zeta omega n, Ts and Tp. So from here, you write the equations, output versus input. Then this is the open loop one without the controller, the GS. So from here, you definitely also can get the performance of it. So this is our second order transfer function. So we need to find the performance of this second order system before we go to closed loop it or we go to design controller for it. So for this open loop second order system, output versus input, to satisfy the standard second order system, you need to get this first. Make sure there is nothing in front of your S square. So from here only you can use the formula s square plus 2 zeta omega n plus omega n square. Then you get the value of omega n and so to the zeta. So from here you can use the formula to calculate the setting time, to calculate the peak time, and to calculate the overshoot as well. So like I said, for this question we do not have the responses, so we choose to use this formula. Okay, so the last subtopic is about time response and its pole location. Pole location, let's look at this cross icon. So when we mark it here, we need to look at this negative zeta omega n, and here imaginary path is the j omega n square root 1 minus zeta square. So this is our pole So this is our pool location, and if you want to rewrite this pools in another way, you also can write in this omega d. So next, what you need to know is, if today I don't have other information and I only have this S plane, so I can try to know the value of theta, because the theta will lead us to get the damping ratio as well. So when I have the zeta and so on, I want to can calculate the peak time, so I can write in this way, omega d, and this is also another way to write zeta d, because you do not need to use the zeta omega n. If you know the location of the pool, you can straight away use this value, and you can straight away use this value to calculate your peak time and setting time. So this is the end of our chapter topic 3.1. Next we will go to steady state error, and please do the exercise in tutorial 3 and those problems in your revision books and textbook as well.